Hi and welcome to John's Maths Book. In this video, we'll be exploring another key concept in mathematics. If you find this tutorial helpful, then please show your support by subscribing, liking, and leaving a comment. Your positive engagement helps me create more content and allows me to bring you more valuable maths lessons. Without further ado, let's go over to the whiteboard. Let's suppose we have a multivariable function where z is equal to f of xy. What do we mean when we want to find its partial derivative? Well, the partial derivative represents the gradient or slope of the tangent line in the direction of the variable being differentiated. This means treating the other variable or variables in the function as constants. So let's say we have a function f of xy which equals x²y². The derivative of f with respect to x, df dx, which has the notation of a curly d, is the derivative of the function with the variable y held constant, and so we only differentiate the x variable. If we go ahead and do this, we can see that the partial derivative of f with respect to x is equal to 2xy², which represents the gradient of the tangent in the x direction for any fixed point y. Similarly, df dy is the derivative of the function with the variable x held constant, so we only differentiate the y variable. If we go ahead and do this, we see df dy is equal to 2yx², which represents the gradient of the tangent in the y direction for any fixed point x. Now let's take a look at this surface f of xy when we plot it in 3 dimensions. So we have our function z equals x²y², which is represented by the surface shown in red. If I now fix a point on the y-axis, so let y equal 1, you can see we have a parabola formed in the xz plane. Using partial derivatives, we can calculate the gradient of the tangent to the parabola at the fixed point y equals 1 and in the x direction. Similarly, if I now fix a point on the x-axis, so let x equal 1, you can see we have a parabola formed in the yz plane. And using partial derivatives, we can calculate the gradient of the tangent to the parabola at the fixed point of x equals 1 and in the y direction. Let's now use the function f of xy, which equals x²y², and look at what that means in terms of limits if we take the partial derivative of f with respect to x. As we saw, when we held y as a constant, this created a parabola shape, and we could then find the gradient of the tangent to the surface in the x direction. On the graph, I've marked point x and x plus h on the x-axis, and their corresponding points on the z-axis where they meet the curve. In this case, I've held y constant at y equals a. If we now draw a secant between the 2 points, we see that it creates a poor approximation to the gradient of the tangent to the curve at point x. If we now slowly reduce the size of h so that it approaches 0, we see the approximation improves and is perfect at the point x where h is 0. So we can say that in the limit as h approaches 0, f of x plus h, a minus f of x, a, which represents this distance here, divided by h, which represents this distance here, represents the partial derivative of the function df by dx when y is held constant at a point a. Let's now calculate the limit as h tends to 0 of the function using these values. So plugging these values into the function x²y², we get the limit as h tends to 0 of x plus h all squared multiplied by a squared minus x²a² all divided by h. Expanding this out, we have the limit as h tends to 0 of a²x² plus 2xha² plus a²h² minus x²a² all divided by h. This term and this term both get eliminated, and dividing both numerator and denominator by h, we see that h is eliminated from the denominator, and this value of h is eliminated, and this term becomes a squared h, which leaves us with the limit as h tends to 0 of 2x a squared plus a squared h. So the limit as h tends to 0 of 2x a squared plus a squared multiplied by h equals 2x a squared. And this represents the partial derivative of the function f with respect to x at a fixed point y equals a, which is the gradient of the tangent to the surface in the x direction when y is held constant at y equals a.